Okay, is my screen visible to you?
Yes, sir.
Fine. Please answer your attendance. Aditya Kumar.
Present, sir.
Anand.
Yes, sir.
Ananda Kumar.
Yes, sir.
Arnachalam.
Yes, sir.
Hasan. Hasan. Hemant.
Present, sir.
Jagan.
Yes, sir.
There's a lot of feedback coming. Can you please mute? Kesu Prasad.
Yes, sir.
Lakshmi Narayanan.
Present, sir.
Prabhakaran.
Present, sir.
Prem Vinayak.
Present, sir.
Rahul.
Yes, sir.
Raujan Kumar.
Present, sir.
Sabish Kumar.
Present, sir. Present, sir.
Okay. Satish Kumar.
Present, sir.
Titus.
Present, sir.
Valish.
Yes, sir.
Vigneshwaran.
Present, sir.
Vijayaraj. Vikash.
Present, sir.
Vivekanand. Yadav.
Present, sir.
Yuvraj.
Present, sir.
Okay, those who have not answered the attendance of Vijayaraj. Then we have Hasan. So Hasan and Vijayaraj are absent today.
Hassan has just joined, sir.
Sir, Hassan has joined, sir. Sorry
Hello?
for being late, sir.
Okay. So Vijayaraj is absent today. Okay. Okay, let us get started. Welcome back. So we are in chapter 3. We are now discussing about SI engine combustion. The last class, I started my discussion on abnormal or knocking combustion in SI engine. So this is one of the undesirable phenomena with regard to the combustion event in SI engine, right? So we discussed the mechanism behind this knocking combustion, how the knocking combustion happens in a SI engine. We discussed about that. So primarily it is concerned with the self-ignition of the N gas. N gas is a charge that is located at the farthest distance from the spark plug. Okay, at any point of time in an SI engine, the ignition has to happen with the aid of flame. Without flame, if there is a self-ignition, then it leads to high pressure rise locally. Okay, and that is what is causing this knocking. Right, mild knock will have vibration, right, in the engine, and it is audible. This knock is audible to human ear. Decibel levels are higher than the human hearing decibel level. So you can hear it, and the engine will also be subjected to vibration. But if it is a prolonged knock, if it is sustained for a longer period of time, it will lead to damage, engine damage. So it's one of the most undesirable phenomena with regard to the combustion event in SI engine. And we need to ensure that the engine runs without any combustion. Engine runs smoothly without any knocking combustion or abnormal combustion. So having understood the mechanism behind this abnormal combustion, which is primarily due to self-ignition of N gas, today we are going to discuss about the effects of this knocking in SI engine. And also we are going to discuss about the various factors that influence the knocking combustion. The idea behind understanding various factors is to handle these factors effectively so that you can avoid knocking combustion. Okay. So these are the effects of knocking in a spark ignited engine. So there will be noise. So you know, noise in an engine are due to two sources. One is combustion based noise and second one is mechanical noise. Mechanical noise is generated by the components. So here we are talking about the combustion noise generated by this knocking, because during knocking the pressurized rate is very high. this high pressurized rate create this combustion noise. Okay, a decibel noise, is measured in decibel. That's a unit. So the decibel levels are high. You can hear the noise. And this noise is primarily due to, I said, when we discussed about the mechanism, knock mechanism. So we understood that the extreme pressure difference create waves, and these waves will go and strike the cylinder wall. Similar to this phenomena is similar to striking the wall with the help of a hammer. Okay, similar to striking the wall with the help of a hammer. Here the waves, pressure waves generated because of the extreme pressure difference that happens during knocking. So you have a main flame traveling in one direction, another flame that start to travel in opposite direction. These two will collide and create severe pressure pulsations as indicated in the pressure profile. And this extreme pressure difference also generate pressure waves. So these waves will strike the wall. Wherever there is a solid boundary, the wave will go and strike the wall and set the wall to vibrate. So that is the source for the noise, combustion noise. Okay, so the pressure waves generate combustion noise and also set the cylinder wall and crankshaft to vibrate. Okay, because of this vibration, there will be rough running of the engine. Right, so when you are traveling in an engine under knocking condition, you can feel that vibration. Okay, so the vehicle, the engine as such will run roughly, and this rough running will also translate into other component. And when you travel in the vehicle under knock condition, you can feel that vibration. So engine runs rough primarily because the waves strike the cylinder wall and set it to vibrate, and the vibration will also get transmitted to the cylinder crankshaft region. Okay, so both valve and crankshaft are set to vibrate during the knocking, and that's what is causing this rough running. So this is one of the undesirable effect. And then we have this mechanical damage. Right, since pressure waves or larger amplitude are generated, it's going to increase the wear of the components which are exposed to the high pressure, high temperature gas. So this mechanical damage will happen primarily to the piston, more specifically piston crown will be subjected to higher wear. Cylinder head will be subjected to higher wear, and then valves will be subjected to higher wear because these are the components, engine components that are exposed to high pressure, high temperature gases during the knocking event. So these waves, pressure waves of larger amplitude are going to hit this component and increase the wear rate. So eventually it may lead to the damage of these components. There will be higher heat loss at the time of knocking. This higher heat loss is due to higher temperature that prevails in the knocking zone. It is also due to increase in the velocity of the gases, right? So heat loss by convective mode is a function of H, A, surface area, and then delta T. Okay, so there is an increased delta T available for heat loss, and H, heat transfer coefficient, is a strong function of velocity of the fluid. So locally you will have a high velocity, and this also enhances the heat transfer coefficient. So overall effect is there will be increase in heat loss at the time of knocking. There will be a higher heat loss, meaning this thermal energy is not available for conversion to work. Basically, from the cylinder, the heat will be lost to the coolant which is circulated around the wall region. So engine has a cooling system, and this cooling system, the primary function of the system is to increase the durability or life. Excessive heat is absorbed by the coolant. Now at the time of knocking, since there is a larger temperature gradient available locally, you will have that will drive the heat transfer from the cylinder gas to the coolant. And also, as I said, the velocity of the gases inside the cylinder is high during the knocking, and that will enhance the heat transfer coefficient, and thereby heat loss will be considerably high. So there will be higher heat loss, meaning that energy is not available for conversion to work. So because of this, you could see that there is a power loss due to the knock event. This is primarily due to higher heat loss. So this is the effect of higher heat loss, that this energy, thermal energy, is not converted to work out of the total fuel energy that is released in the cylinder. Then there is something called pre-ignition. This also happens subsequently due to knocking. Pre-ignition is also called surface ignition. So what will happen due to knocking event is the engine components are subjected to higher temperature. The surface of the component will be at higher temperature, and this high temperature surface is enough to ignite the mixture. Meaning, for example, if you take spark plug, which is exposed to hot combustion gases, at the time of knocking, the temperature inside the cylinder is so high. So the temperature of the components will rise, right? All the solid component temperature will start to rise, right? So this temperature will be high enough when the charge comes in contact with these surfaces. The charge will get ignited because the surface temperature is above the ignition temperature of the charge during the knocking phenomena. So even before you discharge high voltage electric spark, the charge may get ignited by coming in contact with the hot surface. So you have something called hot spots generated in the engine due to knocking event. So you will have surfaces at temperature above the ignition temperature. When the charge goes and get in contact with these hot spots, they are going to get ignited. And so this is an untimed ignition. So you have to precisely control the ignition of the charge by controlling the time at which the spark is discharged. This is important. We discussed about MPT timing, right? So we need to precisely time this ignition event in the engine operating cycle. Otherwise, you will have a problem. So what problem will be there when there is an untimed ignition?
Power loss.
Power loss or emissions.
Power loss will be there, and high emissions, pollutant emission will be there. So the rate of formation of pollutant will be high. I'm going to discuss about that in the second module. After we discuss the pollutant formation mechanism, we will understand that. But here you should note that the more considerable effect is on the power, right? So as I just now said, you have something called MPT timing, wherein we precisely, with the help of control unit, electronic control unit, we precisely time the ignition. Okay, otherwise there will be loss of power. We discuss about this MPT timing, wherein it's a compromise between increased compression work or negative work and loss of expansion work. So this has to be timed appropriately, then only the combustion phasing will be appropriate. Then you can recover maximum work. Otherwise, you will lose major portion or major fraction of the thermal energy release. Right? Untimed ignition will lead to a larger fraction of the energy loss. And because of that, there is a loss of power. Okay, so this is again an undesirable phenomena. This happens subsequently due to knocking, wherein the surfaces are at a higher temperature than the ignition temperature of the charge. So please remember that when we started discussion on this chapter, we said two things. One is ignitable charge, and second one is ignition temperature. Combustion always happen with the proper combination of these two. These two are interlinked. Right? Even if one is absent, there is no ignition, there is no start of combustion. If both are there, there will be ignition. So you already have an ignitable charge that is prepared in the SI engine. Whenever you have a surface which is having a temperature higher than the ignition temperature of this charge, ignition is going to happen. This is what I mean by pre-ignition. The surfaces are rise to the ignition temperature corresponding to the charge equivalence ratio, so that whenever the charge comes in contact with the surface, ignition is going to happen. It's an untimed ignition. Untimed ignition leads to power loss. So power loss during knocking is not only because of heat loss, as we have discussed, it is also due to untimed ignition, due to hot spots that present in the engine. So you will have more, in fact, this pre-ignition event, if it is sustained, then it will also lead to the damage, engine damage, major components will get damaged in the engine. So these are the effects of undesirable effects of this knocking or abnormal combustion event in spark ignited engine. So we need to avoid that. Now let us look at the various factors that influence this knocking. As I said, the idea behind understanding these factors are engine design based variables or engine operating variables. So now we need to look at what are the engine design or operating variable that influence this knocking event. Okay, the idea behind this is once you have an understanding about the factors, you can handle this factor effectively so that you can avoid this knocking which is an undesirable phenomena. Whenever we analyze any factor related to avoiding knocking, you need to remember that this is always due to self-ignition or auto-ignition of the end gas, right? So you need to remember that this event happens due to auto-ignition or self-ignition of end gas. Now let us look at these variables. Okay, I have grouped the variables under 4 categories. One is temperature-based variables. Second category of variables are grouped under density-based variables. And then we have time-based variables. The last one is fuel-based variable. So the factors or variables are grouped under 4 categories: temperature-based, density-based, time-based, and fuel-based. Okay, so under this you have different parameters listed out here. Now let us look at what are these 4 variables. So one is temperature-based. Any factor or any parameter increases the temperature of the end gas. Any parameter in the engine, if it increases temperature of the end gas, then there is a tendency for the knock. Okay, any variable that increases temperature of the end gas, right? You know, self-ignition is primarily due to rising the end gas to its ignitable range. Okay, so when the temperature is rise to the ignition temperature of the end gas, which is already at a particular proportion, fuel proportion, generally this proportion is within the ignitable range. So once you raise the temperature to the temperature of the end gas to its self-ignition limit, then the end gas is going to self-ignite and cause knocking. Those variables are called temperature-based variables as listed out here. So these variables are going to vary the temperature of the end gas. When it increases the temperature, you can expect knocking even. The second variables are grouped under density-based. So any variable, engine variable that increases density of the end gas is going to cause knocking. So density is defined, you know, from the equation of state, it is P by RT. Okay, P by RT is what is density. So any engine-based factor increase, if at all it increase the density of the end gas, then you can expect the end gas to auto-ignite. Can anyone tell me how higher density increase self-ignition tendency?
Sir, higher density means higher volumetric content.
Is it a higher volume or higher mass?
For the same mass of fuel.
It is high mass.
Higher mass, right?
Yes, sir.
So engine has a finite volume, right? So we are now talking about increase in density of the end gas. So end gas is the charge that is located at far away distance from the spark plug. So when I say that end gas is at higher density, it means you have more molecules in a given volume. That is what is meant by higher density. So you know ignition happens, we discuss in chapter 2 when we discuss kinetics, ignition happens at a particular level due to collision among the molecules. So when the molecules are closely packed, you can expect a more number of collisions, and these collisions will lead to radical formation. That is how the ignition will get started. So when there is a larger density, it means the molecules are closely packed. You have more number of molecules in a given volume, and this is going to increase the molecular collision, and thereby it may lead to radical formation and self-ignition. Okay, at the molecular level, this is what is happening, right, at the time of ignition. At the time of ignition, when temperature is high, it increases the kinetic energy of the molecule. So molecular collision increases. When density is high, the molecules, more number of molecules are available in a given space. So you can expect a larger tendency for the collision among the molecule. That's what I mean by density-based factor. Any variable that increase density is going to increase the self-ignition tendency of the end gas. Time-based. So what do you mean by time-based? When you expose end gas to auto-ignition condition or self-ignition condition for a longer period of time. So it's not only about rising the end gas to auto-ignition condition, it's about how long the end gas is exposed to auto-ignition condition for a longer time. If the flame moves quickly and consumes the end gas quickly, then there is no auto ignition of the end gas. On the other hand, if the flame take longer time to reach the end gas, and if the end gas is at a higher temperature, rise to its higher temperature for longer period of time, then you can expect a severe knocking that happens in the engine. So the time of exposure of the end gas to auto ignition condition will play a significant role. And the time of exposure of end gas to auto ignition condition depends on how quickly the flame reaches the end gas. Because the flame gets started from spark plug and it has to reach end gas, which is located at the farthest distance from the spark plug region. That is what we define as end gas. So when the flame moves quickly and consumes the end gas, there is no knock. But when the flame takes longer time to reach the end gas, and if the end gas is at higher temperature, then the tendency for knocking is high. So those factors are grouped under time-based factors. Then we have fuel-based factor. In chapter 1, when we discuss about octane number. Okay, this is one of the most important variable fuel property that affects the knock event in a spark ignited engine. So we need to have a fuel with a minimum octane number. A higher octane number is an indication of anti-knock resistance. So how the fuel resists self-ignition is what is defined by octane number. We discussed this based on molecular composition and molecular structure. But nevertheless, this will play a significant role. This is one of the most important variable. It plays a significant role, and this is grouped under fuel-based. And one is octane number, which is a property, and the second one is equivalence ratio. Equivalence ratio is a proportion of fuel and air. What's the proportion of fuel and air that you have will also affect the knock event. Okay, so these four are the factors. Now let us look at the individual variables in each of these. Right. So when you look at the temperature based factor, one of the most important variable is compression ratio. Compression ratio. So this compression ratio, higher the compression ratio, what will be the tendency for knocking with the increase in compression ratio?
Higher.
Increase, sir.
Increase, right? It is directly correlated. Higher the compression ratio, higher will be the temperature of the end gas because of the higher compression effect, piston compression effect. So you can expect a higher tendency for knocking. Okay, in fact, the maximum compression ratio of SI engine is limited by the knocking event. That's why it is referred to as knock limited compression ratio. The maximum compression ratio is in an SI engine is referred to as knock limited compression ratio. It's generally around 9 to 10. It's not more than that. When you go beyond that, you will have a knocking problem. And this max value is dependent on the fuel octane number. When you use a high octane fuel, for example, currently we use different alternative fuel. Ethanol, if you take, in US, 10% ethanol is blended with gasoline. In any pumping station, if you go, you will have 90% gasoline, 10% ethanol. And ethanol has a higher octane number than gasoline. So the high octane fuel will help you to increase the compression ratio without knocking. Okay, so with the gasoline of a well-defined octane number, there is a max compression ratio. You should not go beyond that. That's why this compression ratio is referred to as knock limited compression ratio. This is one of the most important variables that affect the knocking process. Okay, because higher the compression ratio, higher will be the temperature of the end gas. We have intake temperature. Sometimes we use heating system in the intake line. If you raise the temperature of the incoming charge before it goes into the cylinder, the overall combustion temperature is also going to be high, and that will reflect in the end gas temperature. It's going to be high. So you can say that the tendency for knocking is high when you increase the intake temperature. Coolant temperature. Can anyone tell me how the coolant temperature affect the end gas temperature and knocking?
If the cooling temperature is high, sir, then generally that end gas temperature will be higher side.
When coolant temperature is high, end gas temperature will be high. That's what you are saying.
Yes, sir.
Wall temperature. Wall temperature will be maintained at a higher side.
Higher. Exactly. So, closer to the cylinder wall, you have cooling water jacket, and through the water jacket, you are circulating the coolant, right? We are talking about the temperature of this coolant, right? And its effect on the end gas temperature and knocking. when coolant temperature is high, so there is a heat loss from the gas to the coolant. There is a Q loss from the gas to the coolant, and this heat loss is driven by what? Delta T. Delta T. The gradient available, temperature gradient available will drive the magnitude of heat loss. Higher the gradient, higher the heat loss. As simple as that. Okay. So when you have a coolant at a higher temperature, the heat loss will come down because the gradient available for heat loss is less. Meaning you are retaining more gas inside, more heat inside the wall region. So wall region temperature will rise because of less heat transfer. Okay, so the wall is maintained at higher temperature. So N gas will also be exposed to higher temperature because of this. So higher the coolant temperature, higher will be the N gas temperature because there is a less heat loss. More heat is retained in the cylinder. N gas will be at higher temperature. You can expect that the tendency for knock increases. So higher the coolant temperature, the tendency for knocking increases because you are retaining more heat in the cylinder. Supercharging. So we do supercharging. We go with supercharge engine to increase the power output, right? So what will be the tendency for knocking in supercharge engine? Higher or lower?
Higher, sir.
Higher because supercharging.
Volumetric efficiency.
Yeah, supercharging increase pressure, it increase in cylinder temperature, so knocking tendency will be high because of supercharging. Okay, in supercharged engine, the knocking tendency is high compared to naturally aspirated engine. Naturally aspirated engine, you inject air under ambient pressure temperature condition. Here we use a compressor to increase the incoming air pressure. By doing that, hello? I could get some continuous feedback. Is there something happening? Can you please mute your mic? Also, if there is a hello. Also, if there is a noise happening around, you won't be able to follow. You won't be able to follow my class, right? So you need to create the required ambience. Otherwise, how will you follow the lecture?
Sure, sir. We will ensure, sir. Yeah.
Okay, so other thing I could see here is many of the people are leaving the meeting. I don't know what does that mean. Is it a problem with the network? Or?
So yes, sir, sometimes when we switch in the network, there is an issue. Sir. Like it is, we are reconnecting. It is having some issues.
Okay. Okay, please ensure that, so this is for your betterment, I am suggesting this, ensure that you have the required ambience to follow with the class. If there is a noisy ambience around you, I know you are in the industry and certain things may be out of your control, but ensure that you are sitting in a place where there is no noise and you are able to follow the class. That only will help you, because I'm not sharing the recorded video also. So you need to closely follow. Otherwise, you may miss out what I am teaching. Okay. Okay. So supercharging also increases the pressure as well as temperature inside the cylinder. So you can expect that the end gas temperature will be higher in supercharged engine compared to naturally aspirated engine that has a tendency for knocking. Engine load. So in SI engine, we already discussed that we control load by controlling the quantity of the mixture that enters into the engine cylinder using a throttle valve. High load conditions, you will have more mixture, more fuel air mixture inside the cylinder. At part load, you will have a less fuel air mixture. Since you are burning more fuel air mixture at high load condition, the in-cylinder, as the load increases, the in-cylinder pressure and temperature will also be rise since the burn rate is high. You are burning more charge, more quantity of charge. So N-gas will be at a higher temperature at high load condition. You can expect the tendency for knocking is high at a higher engine operating load compared to the park load operation. Park load operation, the tendency may be less for knock because of the lower operating temperature. Engine load directly affect the operating temperature, thereby N-gas temperature, right? And through this, it affects the knocking even. Spark timing. So when we talk about spark timing, you can have either advanced So always the reference is compression TDC for our analysis. Spark timing may be advanced when the piston is well before TDC. You can discharge electric spark, or it can be retarded. Retarded means when the piston is closer to TDC, it's a retarded timing. So this is retarded spark timing, and this is advanced spark timing. So you can have either of this, retarded or advanced spark timing. Okay. So what will be the effect of this advanced or retarded spark timing on the knock event through the end gas temperature? So we are talking about how this spark timing affect the end gas temperature.
Advanced spark timing will have reduced end gas temperature because the pressure, there is at the beginning of the time, the pressure of the charge will also be a bit lower compared to retarded, because with retarded at the time of spark ignition, like already the charge will be at a higher pressure, and then there are chances that the simultaneous wave front could start from the end of the ball.
Anything else? Okay. Anything else? Any other answer? Do you think retarded timing will have higher tendency or advanced timing?
Advanced, sir, retarded timing, because we will have a delay, means more gap for fuel burning.
I didn't get that. Can you please say it again?
Sir, advanced timing, if we advance the timing, we will have more time duration for the combustion. So in that case, it may have, it may give more knocking tendency, sir.
Yeah. So there are two different answers. One is retarded timing and other one is advanced timing. Okay, which one do you think is correct? Any other response? I got both answers. Which one do you think is correct? Retarded.
Sir, advance will be the correct one basis the flame front propagation and everything. So
perfect. So this is what will have more effect. Advanced timing, not retarded timing. Advanced timing has a higher tendency for knocking, because you need to recollect what we discussed about the mechanism. Okay. So we are forming flame here, it moves and reaches an end gas. Okay. In the advance, this end gas temperature is raised due to several mechanisms. We discussed about that. One is flame compression effect. Second one is heat radiation effect. Right? Flame compression, heat radiation, and pre-flame oxidation. These are the different mechanisms through which the end gas temperature is increased. When you advance the spark timing, this flame compression will be there for a longer period of time. Okay, because you have initiated flame formation in early period of the engine operating cycle. That is what I mean by advanced spark timing. When you delay the spark timing with retarded spark timing, the flame formation is delayed, meaning the compression effect of the flame is relatively less for the end gas. For the end gas, the compression effect will be high when you initiate the flame formation early compared to late. Okay, so with advanced spark timing, you are initiating flame formation early. So flame compression effect on the end gas will be for a longer period of time. Also, the maximum pressure, Pmax value, will be high when you advance the spark timing. So overall effect is in-cylinder pressure and temperature will be higher with advanced spark timing. Okay, and the other effect is the flame compression effect will be for a longer period of time when you advance the spark timing as compared to the retarded. As compared to the retarded case, advanced case will have a higher flame compression time. Okay, because you are initiating flame formation early in the cycle. Okay, so when you advance the spark timing, the tendency for knocking is high because of this reason. Clear?
Yes, sir.
Yes, sir.
Okay, so the next variable is density base. So any engine operating or design base variable increase, if at all it increase density of the end gas, then as I said, you have more molecules, end gas molecule, the tendency for self-ignition is going to be higher because of that. Right, so compression ratio, you know, it affects density. Higher the compression ratio, higher the pressure, as we have defined using the equation of state. Rho is P by RT. When compression ratio is high, P is high, rho will be high. You have more molecules in a given space, so you can expect the knocking tendency of the end gas to be higher with high compression ratio, not only due to temperature effect, also due to density effect. Supercharging, we just now discussed that it is going to increase the pressure, right? So when the pressure of the charge is increased, the end gas density is going to be high. The tendency for knock is also going to be high. As well as engine load, high load, we allow more fuel air quantity to enter into the engine cylinder. So the overall density of the charge is going to be high at high load. So you can expect a higher tendency for the knock. Then we have this time-based factor. So there are two things here. One is the distance traveled by the flame from the spark plug location to the end gas location. When there is an increase in the flame travel distance from the spark plug location to the end gas location, you can expect the end gas to auto-ignite, right? The flame should move quickly and reach the end gas, okay, to avoid knock. If the flame takes more time, if the distance traveled by the flame is more, then that will have an undesirable effect, because the tendency for knock is going to be higher when the flame takes more time, as well as when the flame travels more distance to reach the end gas. So these are the variable. One is cylinder bore. Cylinder bore, you know how the cylinder bore is defined. So when the bore is high, then the flame travel distance will be more. You can expect end gas auto ignition tendency to be higher with a larger bore engine. That's why generally there is an upper limit on the cylinder bore of SI engine. Such limit won't be there for diesel engine. You know, generally it is less than 150 mm in a spark ignited engine, right? Cylinder bore. So there is an upper limit. You cannot keep on increasing the cylinder bore because the flame will travel a longer distance. Any increase in flame travel distance will affect the knock event because to avoid knock, the flame should quickly reach the end gas. That's the idea here. Spark plug location, you can locate spark plug either at the center, or you can have something called the offset spark plug, right? So when you have offset, this is an offset spark plug. In this case, it is at the center. Spark plug is at the center. We prefer to have such a center spark plug located at the center because the flame will travel evenly in both directions. So it will reach the end gas quickly. Whereas in the case of offset spark plug, here it is closer, but the other region is longer, right? So the flame is going to travel longer distance in the other direction. In one of the direction, it is closer, but in the other direction, it's longer. So this longer flame travel distance may increase the tendency for the knocking. So we generally avoid offset spark plug unless otherwise there are some constraint. I will discuss about that when we discuss about the combustion chamber shapes. Okay, so we prefer this central spark plug from the perspective of reducing the flame travel distance. Of course, there are other considerations that we will discuss. Combustion chamber shape. Okay, so when I talk about combustion chamber shape, there are two things. One is piston shape, that is top portion of the piston, and the other one is cylinder head shape. So the cylinder head shape and the piston shape can be of any geometry, right? We are next going to discuss about the combustion chamber design. So the idea here when you shape the piston crown or cylinder head is you need to have a compact combustion chamber so that the flame get access to the end gas quickly. When the flame get access to the end gas by the flame is taking more time, okay, if the flame has to travel a longer distance to reach the end gas, the tendency for knock is high. You need to create a compact combustion chamber shape so that the flame get access to the end gas quickly. Okay, that should be one of the important consideration when you design the combustion chamber. Any increase in the flame travel time will also increase knock tendency. To avoid that, you have to increase the turbulence. If turbulence levels are less, the flame velocity is dependent on we discuss something called a normal flame velocity, right? That's the velocity at which the flame moves. So this flame velocity should be higher so that it quickly reaches the end gas. And that is dependent on the turbulence level in the engine cylinder. Higher the turbulence level, higher will be the flame velocity. and vice versa. If the turbulence is not appreciable, then the flame velocity will be accordingly less. The flame will take more time to reach the end gas. By the time the end gas may reach auto ignition condition and lead to knocking. Engine speed, it's desirable from the perspective of knocking that you run the engine at higher RPM so that the turbulence levels are also dependent on the engine speed, not only the shape of the combustion chamber. The engine running speed will affect the piston velocity, piston speed, and thereby the turbulence levels are affected. Charge motion is affected by the speed also. Higher the speed, higher will be the turbulence. Okay, fluid motion will be enhanced at high engine speed. The flame will travel quickly with the higher velocity that will avoid the knock phenomena. The last one is fuel based. There are two important variables here. One is property, which is octane number. We prefer to have high octane. In fact, there is a minimum octane number requirement based on the gasoline fuel specifications that we have discussed in chapter 1. There is a minimum octane. We should not use fuel below certain octane number value. Otherwise, it is going to cause the self-ignition of the end gas, which will result in knocking. So we need to have high octane fuel from the perspective of avoiding knocking. From the perspective of avoiding knocking, we need a high octane fuel so that the antenna quality is better, the knock resistance is high, meaning the self-ignition temperature is not reached when you have a high octane fuel. Okay, so it will take more time to reach self-ignition temperature by the time the flame will move and consume the end gas. So this is one of the, similar to compression ratio, this is another important variable among all other variables we have discussed so far. This is the second important variable other than compression ratio that affect the knocking event in the SI engine. Next, fuel air equivalence ratio. We have already discussed that the slightly rich fuel air equivalence ratio, is going to create a higher temperature. When the temperature is high, you can expect the knock tendency to be high. So when you run engine with slightly rich mixture, you can expect the tendency for knock is high. Okay, but this is taken care. Generally, we have a close fee range. We already discussed about that. For SI engine, it varies between 0.9 to 1.2. So although the tendency for knock is high around this 1.1, which is slightly rich, it is taken care by other variables like octane number and compression ratio. That's why we don't bother much about this. But nevertheless, you need to understand that this is also one of the variables that is going to affect the knock, right? Slightly rich mixture is creating higher temperatures in the cylinder. So you can expect the tendency for knock is high. So it should be taken care by other variables like octane number and compression ratio. Okay, so these are the various factors that affect this knocking, which is an undesirable phenomena. With this understanding, you know how to handle these variables so as to avoid the knocking combustion in the spark ignited engine. Is it clear?
Yes, sir.
Fine.
Yes, sir.
Now we have moved to the last topic in this third chapter for SI engine combustion. We are going to now discuss about the various combustion chambers for spark ignited engines. So you know this combustion chamber is the place where the combustion event is happening. This is the place where the combustion event is happening in an engine, in an IC engine. Okay, and there are different shapes of the combustion chamber that we are going to discuss. And there are certain consideration you need to give when you are designing a combustion chamber for an engine, because this is very important from the perspective of having an effective combustion event. And we know this combustion event is what is going to affect the performance as well as the pollutant levels in the engine. So you need to carefully design, or you need to carefully optimize a combustion chamber for spark ignited engine. So now we are going to see about what is the design of combustion chamber, what are the factors that you need to consider in order to design a combustion chamber for SI engine. What are the available designs? These are all the parameters that we are going to discuss under this topic, combustion chambers for SI engines. So when we say that we are designing a combustion chamber for SI engine, so what does that mean? So this design of combustion chamber for SI engine include three important factors as listed out here. One is fixing the intake and exhaust valve location. Second one, fixing the spark plug location. Third one, fixing the shape of the cylinder head as well as the piston. Right, so the shape of the cylinder head and piston is going to vary the turbulence level, fluid motion in the engine combustion chamber. Okay, and the spark plug location, just now we discussed that it affects the flame travel distance. You can have spark plug located at different places in the head. Okay, it is basically mounted in the cylinder head. Right, we can have it centrally mounted along the axis, or we can have it offset from the axis. Okay, this is what I mean by fixing the spark plug location. This needs to be carefully optimized, the location of the spark plug, because it affects the flame travel distance. Similarly, fixing intake and exhaust valve location and designing this fixing the suitable place for intake valve as well as exhaust valve will also affect the combustion event. Okay. Primarily, it affects scavenging. It also affects the volume and quantity of the charge that enters into the cylinder. Okay, designing the intake and exhaust valve locations and the specifications of this will affect the quantity of charge that goes into the engine cylinder. Okay, so these are the factors that we consider when we say that we are designing combustion chamber for a spark ignited engine. Right. So what are the considerations to be given for a good combustion chamber design? So these are the major consideration when we design or optimize a combustion chamber. One is higher power output. We need to ensure that with the proper design, we could achieve better performance of the engine as indicated with the increase in the power output. It's not only power output, the thermal efficiency also has to be high, meaning that with a given thermal efficiency, it relates the power output with the energy that we utilize in the engine by burning the fuel. The ratio of these two, power output with the rate of energy input, is what is thermal efficiency. So we need to ensure that we are efficiently converting the input thermal energy into useful power. This is what I mean by higher thermal efficiency. And this is largely dependent on how we design the combustion chamber. Okay, and the third important variable is smoother engine operation without any knocking. Knocking even largely dependent on the shape of the combustion chamber, because shape of the combustion chamber affect the compression ratio, shape of the combustion chamber affect the flame travel distance, flame travel time. Okay, and all this affects the end gas self-ignition. So these are the important variable that affects self-ignition. Just now we discussed about that. So in order to avoid knocking, in order to have a smoother engine combustion chamber design plays a significant role. So these three are the factors that will be considered when we optimize the combustion chambers for a new engine. Okay, when you are involved in the development of a combustion chamber, these three are the primary considerations. So when we talk about higher power output, what are the options we have to increase the power output through the combustion chamber design? The primary factor is compression ratio. In order to have high compression ratio, how do we define, how did we define this ratio, compression ratio, based on the volume, max volume and minimum volume? In simple term, compression ratio is nothing but V max by V minimum in the engine. Max volume by minimum volume is what is compression ratio. It's one of the important design parameter, and it is dependent on the shape of the combustion chamber. So looking at it, so this is max by minimum. Max volume is also called total volume. What is total volume? It's a summation of displacement volume and clearance volume. What is the minimum volume? It's a volume occupied when the piston volume in the cylinder when the piston is at top dead center, which is at the dead center position, and the associated volume is clearance volume, right? So when the piston is here in the top dead center position, the associated volume is clearance volume. Okay, this is a minimum volume, and the total volume or max volume is a summation of this minimum volume and VD. VD is defined based on L and D. L is the stroke length and D is the bore, cylinder bore. Okay, based on that, displacement volume is defined. So when you design the engine, we will optimize. We do a lot of optimization study on fixing the compression ratio for a given SI engine based on a given application. Okay, so we need to carefully fix this volume, clearance volume and displacement volume. Okay, so D and L will decide this VD. VD is nothing but pi D square by 4 into L. This is what is the swept volume, stroke volume or displacement volume. Clearance volume is a volume occupied when the engine, volume of the engine cylinder when the piston is at top dead center position. Okay, it's the minimum volume. Now this minimum volume, that is the volume here in this region, is what is clearance volume. This minimum volume is dependent on one, squiz height. Squiz height is a vertical height between the piston crown and the cylinder head when the piston is at TDC. That is what is the squiz height. So this clearance volume depends on the squiz height. It also depends on the piston shape. It also depends on the cylinder head shape. So you can have a flat piston as shown here, or you can have a bowl. The cylinder head can be flat, or you can have something like this. Different geometries are possible. Accordingly, the clearance volume is going to be different. Okay, so clearance volume needs to be carefully fixed, and it is based on the squiz height, piston shape, as well as cylinder head shape. And VD, once for all, is fixed. You know, VD is what is defining the capacity of the engine. Engine capacity is through VD. In a single cylinder engine, it's 1, N is 1. In a multi-cylinder engine, VD for one cylinder multiplied by N number of cylinder will give the total capacity, total engine capacity. So we need to give a careful consideration when we fix all this volume, displacement volume and clearance volume, right? And we need to optimize this so as to have a higher power output. Compression ratio needs to be increased in order to increase the power output. Okay, so that can be done by increasing Vmax, which is a summation of clearance volume and swept volume. This is primarily done by increasing the VD. The other option is by reducing the clearance volume. Okay, so generally VD is increased because this is what is defining the capacity of the engine. Higher the capacity, larger the power output. So compression ratio is one of the most important variable that needs to be optimized in order to increase the power output of the engine. It's time up. I stop here. If you have, I will continue this in the next class. If you have any questions, I can take your questions now.
Sir, as
Yeah, Prem, please.
sorry, sir, as part of design variable, we are not talking about any thickness here.
Thickness of what?
For example, if the cylinder chamber thickness or wall thickness.
Cylinder wall thickness.
Yes, does that come into play, or when we say design, it is all about the performance-based design variables?
Now here we are focusing on the process, combustion process. Whatever variables we are discussing here under the topic design is for the combustion chamber, right? So it has to do with enhancing the combustion process.
So it is not at the part level design and all.
No. We are focusing on the combustion process. We are discussing all the variables with relevant to combustion process. That's it.
The influence of the other part level design variables also comes into how this behaves, or it doesn't really come into play?
No, with respect to combustion process, whatever we are discussing here are relevant.
Okay, sir. Okay, clear.
Okay.
Sir, one doubt, sir. Is
Sabish, yeah.
Sir, Aditya here. Sir,
Aditya, okay.
Yes, we have discussed, sir, the SI engine, we have a bore dial limit of 150 mm.
Mm-hmm.
So is it only in the case of a single spark plug, or this also applies for multiple spark plug?
Multiple in the sense dual spark plug.
Yeah, dual spark, twin spark.
Dual spark plug, from the flame travel distance point of view, dual spark plug won't have that problem. Okay, from the flame travel distance point of view. So when we talk about effect of one variable, when we want to analyze the effect of a particular variable, we are assuming that all other variables are constant. This is what I said in the beginning also. So from the flame travel distance perspective, right, bore will play a significant role. Meaning I am keeping all other variables as constant. I am talking about what will happen if I increase the cylinder bore. If I increase cylinder bore, keeping all other variables as constant, the flame travel distance will be longer. So from that point of view, I have to reduce the maximum bore, cylinder bore, so that the flame travels for lesser distance.
Sir, if we give a twin spark, then flame will initiate from two locations. So in that case, we can.
Yeah, that doesn't affect it. If you have a dual spark plug, then the bore doesn't have a big influence here. The size of the bore doesn't have a big influence here because you have two flame fronts. So it will reach most of the charge quickly.
Understood, sir. So in that case, also like means over and above this flame reaching time on other parameters, considering other parameters, is it still fixed to 150 mm, or just because of this reason only we are limiting it to 157?
So this is one of the reasons. Here we are discussing from the perspective of reducing flame travel distance, you have a max limit. But generally SI engines are compact, right? You won't have a larger bore, larger stroke or compact. This is the reason why the power output is high, right? Because you don't have any excess air in SI engine, right? It's very compact. Generally we go with lesser D and lesser L.
Understood, sir.
That is also advantages from the perspective of, so diesel engines are larger and bulky, right? So because you need more excess air, almost 30 to 50% excess air we use. So the size is larger. Diesel engines, you cannot have it compact. That's the reason why we cannot design a motorcycle effectively with fueled with diesel.
Understood. Thank you, sir.
Okay.
Sir, am I audible?
Yes, yes.
Just a question, I mean, outside the scope of the learnings, but with regards to how we can remember things. If there is any mind map with respect to what property influences what, there will always be that relationship between one parameter affecting other, right? If there is some reference with you, it would be helpful to understand it as a mind map.
Reference in the sense textbooks.
No, sir, as a diagrammatic representation. For example, we know that one place, if the pressure is going to increase, it is going to affect another property or another physical phenomenon. So something like that, is it easy to have a mind map? It would be easy as a student, I mean.
No, you put the right word, mind map. So it has to come from your mind. You have to synthesize all the information, put it in a way you want to analyze, right? You put a right word here, mind map. So you have information you gather from different sources. It's all about how you synthesize the information and present it in a way you could understand. Okay, so that should come from you. So what I'm saying is I'm giving you information, different information and under different topics. It is up to you to synthesize all the information and bring it in a way you want to analyze.
We'll definitely do that, sir.
What will help you, I will tell you. What is going to help you is you need to know how to correlate one with the other. You might have studied different information in different places under different topics, but try to synthesize and bring it in one place under one common topic so that you will be able to analyze them in a better way. Basically, you have to synthesize information effectively. That has to come from you.
Correct, sir. Agreed. 100% agreed with you. It's just that as a student, I thought maybe it would be available with the professor, so I could ask. So no issues. Understood.
No. See, if I have to take a class, I will put a mind map for myself. What information, in what order I have to present, I have to put a mind map.
Clear, sir. Clear. Yeah. Thanks. Thank you anyway.
Yeah. Okay. Thank you. It's time up. I'll see you on Monday at 6 o'clock. Bye.
Thank you, sir.
Thanks, sir.
Thank you, sir.